All right, 5.1 probability rules. Uh, all right, so first we want to look at random. So the word random suggests an unpredictable result or an outcome. So we usually do simulation and to recreate a random event with these. So we can do those physically, for instance, flipping a coin or selecting things, or allow our computer or calculator, different things virtually to do simulations and run those things based on whatever our need is and what we're doing when we're looking at those pieces. Okay. All right, so for instance here, if we're going to flip a coin 100 times, we would go through and do that simulation. And so we flip the first one and we get tails. But we're looking for heads here on this. And so since we got tails, we got 0 out of 1, or just 0. And then we flip again. This time we do get heads. So that's our second flip. And we can continue that so forth. And so if we did that, we can continue to do those pieces. Okay? And so we end up repeating the process here. And so we see a couple of different things go on with our graph when we're doing that over time. Okay. All right. And so when we look at that random process, we see some things come together. And so the random process represents scenarios of the outcome of any particular trial of experiment is unknown. Okay. So the proportion or relative frequency, so we've seen that before with that, but we're going to call it proportion here, is observed approaches as specific value of the number of trials increases. Okay. Now the probability is the measure of the likelihood of a chance behavior occurring. And so we're going to be looking at short-term results and try to look at those. What do they reveal about long-term predictability with those pieces? That's what probability is all about. Okay. All right, so we have what's called the law of large numbers. And so as the number of repetitions of an experiment increases, so the more times we do something, the proportion with which a certain outcome observed gets closer to the probability of the outcome, so what we think it should be. So the more times we do something, the more theoretical it should become with those pieces. And so we want to see how that happens. And so if we were to actually go back and look at these graphs, we see that both of them over time at the 100 mark end up close to this center line of 50% with those. When we think about that, if we're flipping a coin, it's a 50-50 shot of whether we get heads or tails on that, okay? And so as we do it more and more times, the law of large numbers states that we're going to get closer and closer to that 50% for this flipping coin. And that's all going to be based on whatever our experiment is there. Okay? All right, so in probability, an experiment is any process with uncertain results that can be repeated. So that's anything that we're doing, whether we're selecting things, we're doing flipping a coin, rolling a die, all of those types of things. The sample space is the collection of all possible outcomes, and we typically call that S. An event is any collection of outcomes from a probability experiment with those, okay? And so that'll have a certain type to it when we're looking for those things, okay? Now, simple events we denote with a lowercase e, but in general, we'll talk about our events are going to be with a capital E. And you'll see that in just a minute. All right, so for instance here, rolling a fair die. So what are the possible outcomes of rolling a die? And so that creates our simple events. Rolling a 1, rolling a 2, and so forth, all the way to a 6 on those. So those are all individually things there. If we're going to roll a 1, we're only going to have that one opportunity on those. Now our sample space is all of those possible outcomes. And so 1, 2, 3, 4, 5, and 6. So notice the brackets around that. That is just a set notation. And so we're going to be putting things in those braces, actually, around those. Okay. And so we have 6 possible outcomes for our sample space. Now, notice here we define the event E. So we want to talk about a specific event, and that's rolling an even number. So what is the possibilities for rolling an even number? And so that means that we're going to narrow this down to just the numbers 2, 4, and 6. We know that we have to roll an even, so these are the only possibilities of even numbers on our dice. Okay? All right, now a fair die means that everything has an equally likely outcome, and we typically like to do that. If you go to a casino or something, they should be using a fair die. A loaded die is one where something is has more likelihood of happening, and so if we're more likely to roll a 1 compared to any other number, then we'd say the die is loaded to the 1. All right, so some rules here for probabilities. So our first rule states that every probability must be between 0 and 1. Now it can be 0, it can be 1, but it can't be anything less than 0, so no negatives, and it can't be anything bigger than 1 with those. It has to be a decimal between 0 and 1. We can include 0 and 1. The next thing is that when we add up all of our probabilities, then it must equal 1 for our space there, for our sample space with those. Okay, so the probability of all these samples have to equal 1. Okay, and so if those two things happen, we call it a probability model. And so we got to be able to determine, is the model, what we're looking at, a probability model, and does it satisfy those two rules? All right, so for instance here, we have a bag of M&Ms, and so we want to know, is this table here that we have a probability model? So we look there at our numbers. We see that none of them are negative, so that means they're all bigger than 0, and none of those are bigger than 1. So the first rule has applied for that. So we know that's good, that we're between 0 and 1 for all of those. And then if we were to take and add those together, we see that it equals 1. So rule 2 is satisfied. So therefore, this is a probability model. Now, if either one of those two things don't happen, it's not a probability model. So if we add those together and we get any other number besides 1, if we get 0.99, it is not a probability model. Okay, and so we look for that. If any of those numbers are negative, not a probability. If any of those numbers are bigger than 1, not a probability model. Okay. Now, if we get 0, we would call that event impossible. And so that means it's not going to happen. And so we have those. If we get a 1, that event is certainly going to happen. It will happen on those. And so those are special types. We rarely see those, but it can happen. And then an unusual event is anything that has a low probability of occurring, typically under 0.05 on those, but it's going to be a very low probability. Okay. All right, so computing probabilities. So the probability of an event is approximately the number of times the event is observed divided by the repetitions. Well, that's our relative frequency. We talked about that earlier, that proportion. So it's how many times the frequency of an event divided by the total number of trials on those. Okay, so for instance here, we had 182 drivers, 24 of them had to file an auto policy. So 24 divided by 182 gives us a probability of 0.132 that a teenager will claim an auto policy. Okay, and so we would expect out of 100 drivers, 13 would claim an auto policy. We could also go out there, that's in the thousands place. So out of 1,000 teenage drivers, we would expect 132 of them to claim on their auto policy. All right, so here we have to come up with those things. So what is the probability based on this table? And then we want to look at being able to select some things with those. So what is the probability of somebody being carpooling to work and then walking to work on those types of things? Okay. And so we know that there are 200 total people in this survey. And so in order to find those probabilities, we take each one of the original numbers and divide by 200. So 153 divided by 200, 22 divided by 200, and so forth. And we would get this table here that we have. Okay, and so we've created that probability just by dividing each one of those original frequencies by 200. Okay. All right, so for part B, it says, it asked, what is the probability of an individual carpools to work? And so that was 11 out of 100 there with that, okay, 0.11 for those. And so if we go back to that carpooling, we got 0.11 there for those. And that means that out of 100 individuals, we'd expect 11 to carpool to work. All right. Then the other question asked, would it be unusual for an individual to walk to work? And so that probability was 0.025. And so it would be an unusual because this is a very small number with that, okay? And so that's what we would call unusual. Now the classical method of computing probabilities, it requires equally likely outcomes. And so we work with that. Now it's very similar to what we just did. That's just named a few things differently here, okay? And so it's the number of ways an event can occur divided by the number of possible outcomes. That's still frequency and total amount with those. It's just written differently. Now they use different letters, M and N here. They also use this way of writing it. So we see here the P for probability of an event. N is for the number of event or number in the sample space with those pieces. So we see those letters being used there for those. All right. And so we can do that here with a fair die. We know that we have that equally likely outcome happening. And so we want to look at what's the probability of rolling a 7, a snake eyes, and then we want to comment on those two things there. Okay. So when we look at rolling a die, this is all the possible outcomes. We have 36 with those. And so we can see every possible outcome when we roll a pair of die. Now, what about rolling where it adds up to 7? Well, here are the possibilities. We could roll a 1-6, a 2-5, a 3-4, or a 4-3, a 5-2, and a 6-1 with those, okay? So that means there's 6 outcomes total for that. And so the probability would be 6 out of 36 or 1/6. So we could put that in our calculator and get the decimal with that as well based on whatever they're asking for in our homework. Are they asking for the fraction or asking for the decimal on those pieces? Okay. Now, what about rolling a snake eyes or a 2? Okay, snake eyes means a 1 and a 1. Well, there's only one of those. So when we go back and look here, there's only the very first one is the snake eyes, the 1-1 on that. And so there's only one outcome out of the 36. Okay. So to kind of comment on those, so rolling a 7 we said was a 6 out of 36. Rolling a 2 or a snake eyes is a 1 out of 36. So that means that there is a 6 times likely of rolling the 7 compared to the 2 with those. So out of 36 rolls, we expect 6 7s and only 1 2 in that case. All right, so here's another example. Sophia has 3 tickets to the concert, but Yolanda, Michael, Kevin, and Marissa all want to go with her. So to be fair, she's going to select 2 people. Now she's only selecting 2 because she's the 3rd ticket. So we need to remember that with that. So we need to first come up with a sample space and then compute the probability of Michael and Kevin going to the concert. And then what is the probability of just Marissa going to the concert, no matter who the other person is. Okay. All right, so first our sample space. So we got to do all the combinations of 2 people from that list. So we have here Yolanda, Michael, Yolanda, Marissa, Michael, Marissa, Yolanda, Kevin, Michael, Kevin, and then Kevin and Marissa. So we have 6 possible outcomes here for this, okay? Now, if we're looking at just Michael and Kevin, there's only one of those that say Michael and Kevin, And so that's 1 out of 6 for that. So there would only be 1 out of 6 for our probability of Michael and Kevin being able to attend the concert. Now, what about Marissa? Now, if we go back and look, anywhere we see Marissa's name, we get to pick. And so there are 3 of those that have Marissa's name because it doesn't matter who the other person is on those. So 3 out of 6 or 50% for that. Okay, so we would conclude there that out of 1,000 times, 500 of the times would result in Marissa being able to attend the concert. All right, our next example. Suppose a survey of 500 families with 3 children to disclose the gender of their children had found 180 families had 2 boys and 1 girl. So we want to estimate the probability using our empirical method, meaning based on the information there. But then we want to look at the classical method and compute the probability with that. So being more of our theory with those pieces, okay? All right, so our first one, the empirical method, we want to look at 2 boys, 1 girl. Well, we know there were 180 families out of the 500, so there's a 0.36 probability for this using the empirical. So what they gave us from those. Okay? All right, now what about the classical method? So the classical method, in this case, we need to do a tree diagram so we can see everything. So our first child, we have a possibility of a boy or girl, and then our second child and third child for those, and all the different possibilities here. And so we are creating all of those pieces based on what's happening here. And so we can see this first one is happening because of this line, right? And then the second one is turning right there. The next one is coming this way, and so forth, okay? And so we would have all of those pieces there to create all the different groupings for that. And so all of these are our final sample outcomes for them, okay? And so we'll be able to use those. And we can see there that we have 1, 2, 3, 4, 5, 6, 7, 8 of those, okay? Now, if we're looking for 2 boys and 1 girl with those, then we want to look for all of those pieces. And so this one has 2 boys and 1 girl. This one has 2 boys and 1 girl. This one has 2 boys and 1 girl. And that looks like all of them there with that. So that would be 3 out of 8. Okay, and so that's what we see here when we look at these pieces. And so that's a 0.375. So just a little bit different when we look at the classical compared to the empirical on those. Okay. And so that would tell us that using the classical method, we would expect out of 1,000 tries, 375 to result in 2 boys and 1 girl for those. Okay. And we know that we saw that that happened pretty closely. The 0.375 is very close to the original 0.36 on those. And so they match up pretty closely when we look at the actual event happening. Okay. All right, then the last thing here is subjective. Subjective probability is an outcome based on personal judgment. And so an example of that would be a chance of recession. So that's financial stuff. People don't really know what's going to happen, but they're just saying based on past events, we would expect this. The weather, the chance of rain is going to be personal judgment. It's based off of what they've seen. It doesn't mean it will rain, but it just means that there's a good chance of those things. So those would be subjective probabilities. Okay. All right, so those are the things there we're going to need for 5.1.